You've seen the image, that fuzzy orange ring glowing at the center of our galaxy. They told you it's a black hole. Sagittarius A asterisk, the invisible monster 4 million times heavier than our sun, sitting quietly 26,000 light-years away, pulling everything toward it, letting nothing escape, not even light. But what if that's not what we're looking at? What if the thing at the heart of the Milky Way isn't a hole in space at all, but something else entirely? Something we don't have a word for yet, because right now, in labs most people have never heard of, physicists are running the numbers again. And some of them are starting to say the same strange thing, quietly, almost like they're afraid to say it too loud. Sagittarius A asterisk might not be a black hole. Stay with me, because if they're right, everything you think you know about the center of our galaxy, maybe even the center of every galaxy, is about to change. Let's back up for a second, because to understand why anyone would question something as settled as a black hole, you need to understand what a black hole actually is, not the movie version, the real one. A black hole, in the traditional sense, is defined by one thing: the event horizon, a boundary in space where gravity becomes so extreme that not even light can climb back out. Cross that line and you're gone. No signal, no light, no information ever escapes to tell the rest of the universe what happened to you. That's the promise. That's the deal. A one-way door. And for decades, that idea sat comfortably in textbooks, mathematically elegant, theoretically clean. Einstein's equations practically demanded it exist. So when astronomers pointed the Event Horizon Telescope at the center of our galaxy in 2022 and captured that now famous glowing ring around Sagittarius A asterisk, the world exhaled. Proof. There it is. A black hole. Photographed at last. Except, here's the quiet detail most people missed. The image doesn't actually show a black hole. It shows a ring of light bending around something dark. The darkness in the middle isn't visible because it's a black hole. It's dark because whatever is there isn't emitting light we can detect at the resolution we currently have. The photograph is a shadow, an outline, not a confirmation. And a shadow can be cast by more than one kind of object. This is where it gets interesting, because in theoretical physics, there's a whole quiet family of alternatives that could produce a nearly identical shadow. Objects with almost the same mass, almost the same gravitational pull, almost the same bending of light around them, but without an event horizon, without that one-way door. One candidate is something physicists call a boson star. Instead of collapsing into a singularity, that infinitely dense point at a black hole's core, a boson star is held together by quantum forces balancing against gravity. It's dense, dark, massive, but it doesn't have an edge you can't return from. In theory, you could fall toward it, and if you survive the tidal forces, you might come back out. Another candidate is even stranger, a wormhole. Not the cinematic kind with swirling special effects, but a mathematically valid solution to Einstein's own equations. A throat connecting two distant points in space-time, disguised from the outside as something that looks almost exactly like a black hole. Here's the part that keeps some physicists up at night. When you run the math, the light-bending signature of a wormhole mouth can look nearly identical to a black hole's shadow. Nearly identical, not exact, and nearly is where the real question lives, because if you can't yet see the difference, how do you know which one you're looking at? This isn't fringe thinking either. It isn't a conspiracy theory dressed up in equations. Papers exploring these alternatives have appeared in respected physics journals for years, written by researchers at real institutions, using the same mathematical framework that gave us black holes in the first place. They're not saying black holes don't exist elsewhere in the universe. They're asking something narrower, and somehow more unsettling. Are we sure, really sure, that Sagittarius A asterisk specifically is a one? And when you start pulling that thread, you find something that should surprise you. We've never directly proven the presence of an event horizon anywhere. Not once. Not for Sagittarius A asterisk. not for any black hole candidate we've ever observed. We've inferred it. We've assumed it because the math fits, because the shadow looks right, because it's the simplest explanation that matches what our instruments can currently detect. But simplest explanation and only possible explanation are not the same sentence. There's a difference between what's likely and what's proven. And the center of our galaxy has been sitting in that gap for a long time, letting us believe we'd solved it. So if we've never actually confirmed an event horizon, what have we confirmed? Let's talk about what we actually know for sure, because it matters. In the early 1990s, astronomers began tracking a handful of stars orbiting something invisible at the exact center of the Milky Way. Over decades, literal decades, patiently, one observation at a time, they watched those stars trace out orbits. Tight, fast, gravitationally violent orbits around nothing visible at all. One star, given the unglamorous name S2, swings so close to Sagittarius A that it reaches speeds of almost 3% the speed of light. 3%, around something we cannot see. That discovery alone eventually won a Nobel Prize in 2020, because the only way to explain orbits like that fast, that tight, around that much invisible mass, compressed into that small a region of space, is if there's an object there with roughly 4 million times the mass of our sun, packed into a space smaller than our solar system. That part isn't up for debate. The mass is real. The gravity is real. Something enormous and dark sits there, bending the paths of stars like a hand stirring water. What's up for debate is what that something actually is. And this is where I want you to sit with a strange kind of humility for a second, because we like to think of astrophysics as a finished science, as if we're just filling in decimal points at this stage, tidying up details. But the truth is messier and more honest than that. We are still, in many ways, staring at shadows and guessing at shapes. Think about it this way. Imagine you're standing outside a house at night. Every window is dark. You can't see inside. But you can hear things. Footsteps, a chair scraping, a door closing somewhere deep in the structure. From those sounds alone, you start building a picture of what's happening inside. You develop a theory, maybe even a very good one. But you haven't seen inside the house. Not really. That's where we are with Sagittarius A*. We can hear the footsteps, the orbits of stars, the bending of light, the faint flickers of matter spiraling in before it disappears from view. We've built an extraordinary, mathematically consistent theory from those clues, but the door has never actually opened. We've never confirmed with certainty what's standing on the other side of that darkness. And here's the detail that quietly haunts a lot of physicists working on this. Even the 2022 image, the one plastered across headlines worldwide, required an enormous amount of processing to produce. Radio telescopes scattered across the globe, from Antarctica to Spain, synchronized down to the nanosecond, gathering data for years, and then algorithms filled in the gaps between what was actually observed. The final image wasn't a photograph in the way you photograph a face. It was a reconstruction, an interpretation built from fragments, guided by the assumption that a black hole was what they'd find. That doesn't make it wrong. Reconstructions can be accurate, interpretations can be correct, but it does mean something important. What we call proof, in this case, is really our best current model wearing the costume of certainty. And once you notice that, you start noticing it everywhere in this story. There's a particular kind of fear that lives underneath this whole conversation, and it's worth naming because it explains why the alternative theories feel so unsettling to some people and so thrilling to others. The fear is this: if Sagittarius A* isn't a black hole in the way we imagined, what does that mean about everything else we think we understand? Because black holes aren't just an interesting curiosity sitting at the center of galaxies. They're load-bearing walls in modern physics. They're the places where Einstein's general relativity gets pushed to its absolute limit, where gravity becomes so extreme that our equations start to strain and bend, almost like they're warning us we're standing somewhere we don't fully belong yet. If the object at the center of our galaxy turns out to be something other than a classical black hole, a boson star, an exotic compact object, something genuinely new, it wouldn't erase Einstein. His equations would still hold up beautifully everywhere else they've been tested for over a century now, without failure. But it would mean that one of the most iconic proofs of extreme gravity in the popular imagination was actually pointing at something science hasn't fully named yet. And there's something almost beautiful in that possibility if you let yourself sit with it instead of resisting it, because science doesn't actually move forward by being right all the time. It moves forward by being wrong in interesting, specific, correctable ways. Every major shift in our understanding of the universe, from a flat Earth to a round one, from a fixed universe to an expanding one, from Newton's gravity to Einstein's warped space-time, started with the same quiet, uncomfortable sentence. What if the thing we assumed isn't quite right? That sentence isn't failure. It's the whole engine of discovery. Here's what makes this particular mystery so hard to resolve, though, and it's not a lack of intelligence or effort. It's distance. 26,000 light-years is almost incomprehensible as a number, but think of it like this. The light reaching our telescopes right now, showing us Sagittarius A asterisk as it appears today, actually left that region of space before humans had built the first cities. Before writing existed, before agriculture spread across most of the world. We're not looking at the center of our galaxy as it is. We're looking at an old photograph and calling it the present, which means even if there were some subtle difference between a black hole and, say, a boson star, some faint signature in how light bends or how matter behaves right at the edge, the difference might be so small and the distance so vast that our current instruments simply cannot resolve it yet. Not won't, can't, not yet. This is the part that separates real scientific uncertainty from the internet's version of nobody really knows anything. Physicists aren't saying black holes are a hoax, or that Einstein was wrong, or that we should throw out a century of evidence. What they're saying is far more precise and far more interesting. Our current data is consistent with more than one explanation, and until our instruments improve enough to rule the alternatives out, intellectual honesty means holding the door open. Holding the door open is not the same as being lost. It's the opposite, actually. It's what real understanding looks like from the inside. Messier than certainty, but far more alive. So let's go back to that ring of light, the famous image, because there's a detail buried in it that most headlines skipped right past. And it's the detail that scientists chasing the not a black hole theory keep coming back to. The ring isn't uniform. It's brighter on one side than the other. Slightly lopsided, slightly uneven, like a coin that didn't land perfectly flat. For a classical black hole, that asymmetry is explained easily enough. It's the result of matter swirling around it at incredible speeds, with the side rotating toward us appearing brighter than the side rotating away. An effect called relativistic beaming. Simple, expected, textbook. But here's the thing about textbook explanations. They're built to fit what we already believe. And a handful of researchers have gone back to that same asymmetry and asked a quieter, more uncomfortable question. Does it fit just as well, or maybe even better, with something that isn't a black hole at all? Some early modeling suggests certain boson star configurations could produce a similar lopsided ring without needing an event horizon to explain it. The light wouldn't be bending around the edge of a one-way door. It would be bending around the surface of something dense, dark, but ultimately survivable, something with a there instead of an absence. I want to be careful here, because this is exactly the point where popular science videos tend to oversell a theory to make it sound more dramatic than the evidence supports. So let's be precise. Nobody has proven Sagittarius A asterisk is a boson star, or a wormhole, or any other exotic object. What's true is narrower and, honestly, more interesting. the current data doesn't yet rule those possibilities out. And in science, an unruled out alternative isn't nothing. It's a live question, sitting right there in the room with the accepted answer, waiting to be either confirmed or eliminated. This is where a quieter kind of tension enters the story. The tension between what's comfortable to believe and what's actually been demonstrated. Most of us, without realizing it, treat well-established and proven beyond doubt as the same thing. They're not. Plate tectonics was well-established science for decades before we had a full mechanical explanation for exactly how continents moved. Evolution was overwhelming, well-supported science long before we could sequence DNA and watch the mechanism directly. Being well-supported and being fully understood in every detail are two different stages of the same journey, and it's completely normal, expected even, for something to sit in that gap for years, sometimes generations. Sagittarius A asterisk is right now somewhere in that gap, and here's something worth sitting with for a moment. Even the scientists most confident that it is a black hole would tell you, if you ask them honestly, that confident is not the same as certain. They tell you that the Event Horizon Telescope collaboration itself has been transparent about the limits of their data, about the assumptions baked into their models, about the fact that ruling out every alternative wasn't the goal of their 2022 announcement, demonstrating consistency with general relativity was. Consistency with a theory is powerful evidence. It is not the same as elimination of every other possibility. So what would it actually take to know for sure? What separates probably a black hole from definitely a black hole in a way rigorous enough to satisfy the physicists still holding the door open? It comes down to resolution, literally. The Event Horizon Telescope network is already being upgraded with new stations, sharper synchronization, and plans to eventually observe not just a single frozen image, but something closer to a live sequence, capturing how the shadow shifts and flickers over time, the way matter actually swirls and falls in real time, rather than one static snapshot standing in for years of data. If Sagittarius A asterisk has a true event horizon, that flickering should behave in a very specific, mathematically predicted way. If it's something else, a boson star, a wormhole mouth, something without a true point of no return, the flickering might behave subtly differently. Slower here, sharper there, a pattern that shouldn't exist if the textbook explanation is complete. We are, quite literally, waiting for the universe to blink so we can watch how the shadow moves. There's something else worth sitting with here, something that goes beyond telescopes and equations. It's the question of why this particular mystery grips people the way it does, why a fuzzy orange ring at the edge of comprehension makes so many of us stop scrolling. I think it's because Sagittarius A asterisk sits at the intersection of two things humans have never stopped needing, an answer and a mystery. We want both at the same time, which is a strange thing to want. We want to know, and we want there to still be something left to find out. For most of human history, the center of the galaxy wasn't even visible to us. A smear of light in a dark sky, unreachable, unknowable, filed away under the heavens, a word that used to mean something closer to myth than measurement. It's only in the last 100 years that we've had the tools to even ask the right questions about it. And it's only in the last few years that we've had a picture, blurry, reconstructed, imperfect, but real, of the exact spot where 4 million suns worth of mass seems to vanish from view. That's an extraordinary thing to hold in your mind, if you actually stop and let yourself feel the scale of it. Not just intellectually understand it, feel it. 26,000 light-years away, at the gravitational heart of the galaxy that contains every person you've ever loved, every mistake you've ever made, every ordinary Tuesday you've ever lived through, there's something we still cannot fully name. And maybe that's the part that unsettles people more than the physics does. Not the math, not the equations. The fact that certainty, the thing we reach for instinctively, especially about the biggest questions, might not be available yet. Might not be available for a long time. But here's a different way to hold that same fact, one that doesn't feel like loss. Every generation of scientists has stood exactly where we're standing now, at the edge of what current instruments can resolve, squinting at a shape they can almost, but not quite, confirm. Galileo squinted at smudges of light and called them moons of Jupiter, and it took decades for anyone to fully believe him. Astronomers in the 1920s argued for years about whether the spiral nebulae they saw through their telescopes were part of our own galaxy, or entirely separate galaxies, millions of light years away, that we now call home to as much life as the imagination can hold. They were standing exactly where we stand now with Sagittarius A asterisk, almost sure, not yet certain, living in the gap. And every single time, eventually, the gap closed. Not because someone got lucky, but because someone kept building better instruments, asking sharper questions, refusing to let probably quietly calcify into definitely without earning it first. That's what's happening right now. In observatories most of us will never visit. With data most of us will never read firsthand. Physicists refusing to let the most famous image in modern astronomy get treated as a final answer when it might only be a very, very good first draft. There's a kind of quiet integrity in that. In looking at something almost everyone else has already decided is settled, and saying gently but firmly, not yet. Not until we've actually ruled out the alternatives. Not until the door has really opened. By the way, if you've made it this far with me, I'd love it if you hit subscribe and stuck around. This channel is for exactly this kind of question, the ones that live in the gap between what we assume and what we've actually proven, and we go looking for that gap almost every day. I'm curious, if it turned out Sagittarius A asterisk wasn't a black hole at all, what do you think it would change about how you see the night sky? Drop it in the comments. I actually read them. Okay, back to the center of the galaxy, because there's one more thread worth pulling. Here's the thread I want to pull, and it starts with a question most people never think to ask. How would we actually know if we were wrong? Not wrong in the sense of a rounding error. Wrong in the sense of having mistaken one kind of object for a fundamentally different one, hiding in plain sight, 26,000 light-years away. The answer, it turns out, is gravitational waves. In 2015, for the first time in human history, we detected ripples in space-time itself, the aftershock of two black holes colliding billions of years ago, finally reaching Earth as a signal so faint it required instruments sensitive enough to measure a distortion smaller than the width of a proton. That detection confirmed something extraordinary. Black holes, at least somewhere in the universe, really do exist, really do collide, really do leave behind exactly the kind of signature Einstein's equations predicted a century earlier. But, and this is the detail almost nobody outside physics circles knows, a boson-star merger, or the collision of other exotic compact objects, might leave behind a gravitational wave signature that looks almost identical to a black hole merger in its early stages, and then diverges, subtly, at the very end, in what's called the ring down, the moment right after collision when the newly formed object settles into its final shape. A black hole's ring down follows an extremely specific mathematical pattern, one tied directly to the existence of an event horizon. An object without a horizon should ring differently, not wildly differently, but measurably, if our instruments are sensitive enough to catch it. We are right now in the earliest years of being able to listen for that difference at all, which means the real answer to the Sagittarius A asterisk mystery might not come from a telescope pointed at the galactic center at all. It might come from somewhere else entirely, a gravitational wave detector catching the ring down of some completely different collision elsewhere in the universe that finally tells us definitively what an object without an event horizon actually sounds like. And once we know that signature, we can go back and ask, with far more precision, does Sagittarius A* behave like something with a horizon or without one? Science rarely solves its biggest mysteries where it first found them. It solves them sideways, an answer arriving from a direction nobody was originally looking. And that, maybe, is the real shape of this story. Not a single dramatic reveal, not a headline that suddenly declares "black hole debunked." Something slower, quieter. 100 small pieces of evidence gathered from 100 different directions. Telescopes, gravitational wave detectors, decades of stellar orbits. Theoretical models refined over and over, slowly narrowing the space of what Sagittarius A* could possibly be, until eventually, almost without anyone noticing the exact moment it happened, the answer becomes obvious in hindsight. That's how most of science actually works. Not lightning bolts of discovery. Erosion. Patient, relentless erosion of uncertainty. One measurement at a time. We're still in the erosion phase with Sagittarius A*. And there's something honest, even moving, about admitting that out loud, instead of pretending the photograph settled it in 2022. So here's where we actually are. Not certain, not lost either. Somewhere in between, in that strange, honest place science lives most of the time, even when it doesn't sound like it in headlines. Sagittarius A* is real. Its mass is real. 4 million suns compressed into a space that shouldn't be able to hold that kind of weight, bending the paths of stars we've watched for 30 years now. That part isn't in question. What's in question is the nature of the thing itself. A black hole with its one-way door and its point of no return. Or something else. A boson star. A wormhole mouth. Something without a name yet, waiting at the edge of what our instruments can resolve. Maybe by the time better telescopes arrive, better gravitational wave detectors, sharper eyes turn toward the center of our galaxy, maybe it turns out to be exactly what we thought all along. A black hole, textbook and true, and the whole conversation becomes a footnote. A moment where science briefly doubted itself, and then confirmed what it already suspected. Or maybe not. Maybe the thing sitting at the heart of the Milky Way, the thing every star in this galaxy quietly orbits, including the one we call the Sun, including the planet under your feet right now. Maybe it's something we haven't even properly imagined yet. Something our equations gesture toward but can't yet name with certainty. Either way, here's what doesn't change. 26,000 light-years away, right now, tonight, something enormous and dark is holding an entire galaxy together. Holding us together, in a sense. And we still don't fully know what it is. Most people will never think about that again after this video ends. They'll close the tab, scroll to something else, let the mystery dissolve back into the noise of an ordinary day. But you didn't close the tab. You stayed until the shadow stopped being just an image and started being a question. That's the part I hope you carry with you tonight, the next time you look up. If this pulled at something in you, subscribe and share it with 5 people who'd want to sit in that same gap with us. And I mean it. Tell me honestly in the comments, does not knowing bother you, or does it feel like something else? And if there's a question like this one, something sitting unresolved at the edge of what we understand that you want us to go looking for next, tell me. That's exactly what this channel is for. Until next time.